So I'd like to welcome Ken Burns and introduce him. He'll introduce our speaker and our session for today. Thank you for being with us.
Thank you, Julie. I'd like to introduce Dr. Arun Srivastava. Dr. Srivastava is one of our distinguished professors at the University of Florida. He got his PhD in India at the Indian Institute of Sciences in Bangalore. And then he came to the US to do a postdoctoral fellowship at the Sloan Kettering Research Institute in New York. Following that, he actually came to work at the University of Florida in our laboratory for a couple of years, where we introduced him to AAV, or adeno-associated virus, with which he has remained over the years and become a real leader in the field. While I was out of the country for a year on sabbatical, Dr. Srivastava disappeared and wound up in Little Rock, Arkansas, at the University of Arkansas Medical Center. Anyway, after just a couple of years there, we got him into Indiana University Medical School in Indianapolis, where he rose through the ranks to become professor of microbiology. Very successful, so successful that the then chair of Pediatrics, Terry Flott, recruited him back to the University of Florida with an endowed professorship, the George Kitzman Chair, as the head of the Division of Molecular Therapy, which he has continued to lead since about 2004. He's had some real all-stars in the division, and they've made great progress on the development of AAV as a vector for gene therapy. Now, in this course, Dr. Srivastava is going to give two talks. The first talk is today, and he's going to talk about gene therapy in a general sense, the principles and what it's useful for. And then at the end of the course, he's going to talk about a couple of situations where AAV has been used as a vector for gene therapy of people with actual diseases, and the vector has actually worked very well and cured those diseases in several instances. So I don't want to give his whole talk. So at this point, I'll turn the floor over to Dr. Srivastava. Arun.
Thank you so much, Dr. Burns, for your very kind words. And, I've made several mistakes in my life, obviously. But one of the biggest mistakes was, leaving Dr. Burns's lab too soon. I wish I could go back in time and stay with him forever. So having said that, let me just get started here. So today I'd like to take a bit of a time and talk about the brief history of gene therapy. I'm sure most of you are very familiar with this, but I'll just take you through the entire journey. So what is gene therapy? So this is the Scientific American definition, and this was an article published by Dr. Indra Verma. It was at Salk Institute at the time. He published this article in the September 1990 issue of Scientific American. It's a gene therapy, treatment of disease by introducing healthy genes into the body. So how do you do that? How do you deliver genes into the body? And one way to do this is to use a virus. I'm sure you're very familiar with all the viruses. So this is the article I was talking about. This is by Dr. Indra Verma, published this in Scientific American in September issue of 1990. Gene therapy, the treatment of disease by introducing healthy genes in the body. And the way one delivers genes into the body is by using a virus. And these are some of the examples of the known viruses. This is one of the largest virus called pox virus. It's used to cause smallpox. This is herpes virus, causes herpes. This is adenovirus, very common infection in humans. And this is a retrovirus. And so adenovirus and retrovirus is what we will talk about today, and AAV next month. And I'm sure you're all very familiar with the coronavirus, which is shown here. And this is a large virus which causes Ebola. So, so again, this is a picture taken from a review article written by Dr. Theodore Friedman, published in Scientific American in June 1997. This is what, if you break open, this is what a retrovirus particle looks like. And this is the first virus that was used to deliver genes into humans. So the very first gene transfer in humans was performed in 1989 at the NIH by Dr. Steven Rosenberg and his colleagues. So they took T cells, peripheral T cells from patients and infected them with the mouse retrovirus, which I just showed you, carrying a marker gene called the neomycin gene. So this was not really gene therapy, this was gene transfer. So this obviously has no therapeutic value. So they took these tumor-infiltrating lymphocytes, infected them with the retrovirus carrying this neomycin gene, and then reinfused them into patients who had advanced melanoma or skin cancer. And they showed that in the 5 patients that received their own T cells, the gene-modified cells were in circulation from anywhere between 3 weeks to up to 2 months. So this established the principle that perhaps genes could be delivered back into the patients using their own cells, and of course, using a retroviral vector. So the very first human gene therapy trial in humans was performed on September 14th, 1990. And this is for a disease called severe combined immunodeficiency, or SCID. And this disease is caused by the loss of the absence of an enzyme called adenosine deaminase, or ADA. And as a result, these patients don't have any functional B or T cells which fight off infections. So this trial was done by 3 doctors here, Dr. French Anderson here on the left, Dr. Ken Culver, who was actually a fellow, he did the actual infusion. And this is Dr. Michael Blaze. This is a 4-year-old girl. Her name is Ashanti da Silva. She was the very first recipient of gene therapy. So they took her T cells, actually bone marrow cells, infected them with the retroviral vector carrying the ADA gene, and reinfused those cells back into her. And I was able to find a couple of images. A year later, 1991, this picture was taken. Again, you can see she's thriving. She's Ashanti da Silva. She's now 5 years old. And this is Dr. French Anderson, Dr. Michael Blaze, and Dr. Ken Culver. Actually, a few months after Ashanti received her treatment, a 10-year-old girl named Cindy Kissick also was treated. And she's now, at 1991, she was 11 years old. And both girls seem to be thriving. And the last image I was able to find was in 2013. Ashanti da Silva is now 27 years old in 2013. This is Dr. Michael Blaze, and this is Cindy Kissick, who's 33. And this year, Ashanti da Silva turned 36, and Cindy Kissick now is 42. So you can imagine that, these kids would not have survived without gene therapy, because this is a deadly disease. These patients cannot fight off infections. So I'll let Ashanti da Silva tell you her own story in her own words. And she gave an interview on June 7th, 2018. And this is a very brief video of her.
life as a human guinea pig. And at the risk of being too cute and clever, that is essentially the story of Ashanti da Silva, who is also the rare disease editor at an outlet called The Mighty. Ashanti, thank you so much for being here at the BioBus Center.
Thank you for having me.
So why don't we start by you sharing your medical history, your story,
Sure.
please?
Yeah, I was born in '86, and 2 years later, after seeing about 40 doctors, I was finally diagnosed with severe combined immunodeficiency, which is a rare type of immune deficiency. And it used to be referred to as bubble boy disease. So basically no functioning immune system, no T cells, no B cells, no NK cells. And I was falling sick all the time. So it really was amazing, especially in the 80s, to get a diagnosis, a rare one. So I feel very lucky. At that time, the only thing available was enzyme replacement therapy, which is what I was put on. Even that was in a clinical trial phase. I was one of the first people to be put on that. And it worked for a while. And after about 2 years, the effects of the enzyme replacement therapy was wearing off. And I really needed something else. Otherwise, I was slipping away. And the doctor who had diagnosed me, Dr. Sorensen in Cleveland, Ohio, he had said, there's this trial going on potentially at the NIH. And they're considering SCID ADA. So let me just send over her blood.
And what is that?
Sorry, what is...
You were saying, you just mentioned an acronym or an abbreviation.
Oh, sorry, severe combined immunodeficiency. And so let me send over her blood. No guarantees, don't get your hopes up, but who knows, maybe in her lifetime. That's what they told my parents. So my mother continued to have hope. My father was like, this is never going to happen. And they were lucky enough in 1990 to get a call from the doctors who were working on it. And they chose me to be the first recipient of gene therapy.
First patient in the world.
The first patient in the world. Yeah, it was really amazing. And I'd like to highlight that one of the reasons they chose my family, I think when there's such like a controversial treatment, it's really important to take many things into consideration. One of those things the doctors were considering was, would the family understand some of the science behind this? Would they be able to ask the right questions? And I was lucky that my father was a chemical engineer and my mother was a nurse. So they were involved every step of the way,
So here you are, all those many years later, clearly healthy and thriving. And now you're working, as I mentioned, at the Mighty. So for people who aren't familiar with that, tell us about this outlet.
Yeah, it's been amazing to work at the Mighty. I actually found them online a year before I started working for them in 2016, when I was newly diagnosed with another rare condition. And it was the first site I had ever seen where it's stories about conditions written by patients themselves or written by family members who have someone with that condition in their family. And it was really powerful because I think oftentimes when you're newly diagnosed with any condition, you will go to a site like Wikipedia or WebMD. Dr. Google. And it's very impersonal and it feels even more isolating when you're just looking at symptoms and what can happen to you. And especially with a rare disease, it's very hard to find those connections and find people you can actually relate with. And I found that on the Mighty. So for a year after I was newly diagnosed, I followed them. And it's been wonderful working for them. We're now the largest digital health community. We have over 1.5 million members.
Wow.
Yeah.
That's great. Congratulations.
Oh, thank you.
So now from that back to you to see the explosion, the beginning of the fulfillment of the promise of gene therapy, actually coming to reality, coming to fruition. What that's like for you having been patient zero in that field.
It's amazing to see it have come full circle from the first trial ever in the world to now it's, being sold and it's a commercial therapy being used. And this is what my parents and I had hoped. And obviously the doctors and researchers behind this is that it would be used to treat many conditions. To see it go beyond SCID ADA, the condition that I have, is really amazing. And I have a lot of hope for where it's going to go. And I'm excited, anytime that I can to really be an advocate for gene therapy because it really has saved my life.
That's awesome. You and a lot of people have a lot of hope, and now we're seeing that hope translated into reality.
Yes.
Shanti Da Silva, thank you so much for being here at the BioBus
Thank
Center. And
you.
if you want to read more from her and her teammates, go to themighty.com.
Thank you.
Okay, so she's obviously thriving thanks to gene therapy. The next successful gene therapy trial was done by Jim Wilson at the University of Pennsylvania. This was a disease called familial hypercholesterolemia, where these patients have very high levels of cholesterol circulating in the blood because they have this receptor that is missing. So Dr. Wilson isolated hepatocytes liver cells from a 29-year-old Canadian woman whose cholesterol levels were extremely high, 400 milligrams per deciliter. Normal range is around 100 to 150, and very high risk for stroke and heart attacks. So her liver cells were then infused with the retroviral vectors carrying the LDR gene, the lipoprotein, low density lipoprotein receptor gene, and these cells were infused back into her body. And this patient was followed for 18 months, and you can see her level dropped from 482 down to 366. So this was, of course, this was not curative, but it provided again other evidence that this perhaps could work. The real success story came out of this trial with the ADA SCID. This was a trial done by Claudio Bordignon and Fulvio Movilio in Italy, where they took 2 patients with ADA, the adenosine deaminase deficiency. They took their T and bone marrow cells, and then they infused them with the same retroviral vector, and then they followed these patients for 2 years and saw clinical benefit. And the original trial that was done at the NIH by Doctors Michael Blaise, Ken Culver, and French Anderson, in this trial, they treated 2 patients, as I mentioned before, Ashanti Da Silva and Cindy Kissick, and they followed these patients for 4 years and showed clinical benefit. And you can see in the video already they are doing well. And then the next trial was actually done by Don Cohn at University of Southern California and Robertson Parkman. They actually took umbilical cord blood cells from neonates and treated them with the same vector at early stages, the neonates. And you can see this time they took their stem cells, the CD34 positive cells, and showed the long-term survival of T and B lymphocytes for up to 18 months. So this was proof positive that this could be actually done at very early stage in life. And then another same group in Italy, Alessandro Aitui and Claudio Bordignon, they used stem cells instead of T cells, and this time they used non-myeloablative conditioning, so without having to kill the bone marrow. Again, they showed that in 2 patients, these cells were transduced with the vector, and they showed improved immune functions for about a year or more. So this was looking really positive. Then they moved on to a more serious disease called the X-linked severe combined immunodeficiency. And this trial was done by Marina Cavazana-Calvo and Elaine Fisher in Paris. So this is a more serious condition. And fortunately, they showed that this time, of course, the gene is a different one called IL-2 gamma receptor. They treated 2 patients, again, their stem cells, and again, their T, B, and natural killer cells function was improved. They followed these patients for up to 10 months. So this was looking very promising. And then the same group in France showed that sustained correction of X-linked severe combined immunodeficiency by ex vivo gene therapy. And this time they treated 5 boys. And again, they followed these for much longer time period, 2.5 years, and showed clinical efficacy. Another bone marrow failure disease called Wiskott-Aldrich syndrome. This trial was done by Kahn Bartzuk and Christoph Klein in Germany, and they showed clinical efficacy in 2 patients. The gene is called WASP for Wiskott-Aldrich syndrome. Again, these patients were followed for 2 years and showed normal T, B, and natural killer cell functions. So again, not only severe combined immunodeficiency, but a different bone marrow failure disease could be cured by retroviral vectors. So back to this article by Dr. Verma, in his last paragraph, he actually said this. He said, in spite of the advent of retroviral vectors that cannot replicate, there is still a chance they could cause cancer, because that's what retroviral vectors do. They cause cancer in mice. So unfortunately, Dr. Verma had seen the future, and this is exactly what happened. So I'm going to take you through a few slides where this first evidence of tumors or cancer was seen in patients with X-linked SCID. This is the Alain Fischer-Cavazana-Calvo trial in Paris, where T-cell leukemia was observed in 2 patients 3 years after they received their gene therapy. So the mouse retroviral vectors were causing leukemia. They were cured the disease for X-linked SCID, but they were causing T-cell leukemia, unfortunately. And this was not only limited to France, it also happened in London. This was a trial done by Steve Howe and Adrian Thrasher. Again, exact same disease, X-linked SCID, and same retroviral vector. They saw T-cell leukemia occurring in 1 out of 10 patients 2 years after gene therapy. And it got worse. This is a trial again done in France by Alain Fischer and Marina Cavazana-Calvo. This time they saw T-cell leukemia in 4 out of 9 patients. So in 3 geographically different locations, same vector, same disease, several patients now develop T-cell leukemia, much longer follow-up, 31 to 68 months after gene therapy. So the picture was emerging that retroviral vectors, although they can cure your disease, they are not safe because there's a risk of developing leukemia. This also happened in another disease called chronic granulomatous disease, and several oncogenes were activated. This trial was done in Germany. MDS1, EV1, PRDM16, and ZBP1 genes were activated. This was a trial in which 2 patients, adult patients, were treated with this disease, and 3 months after gene therapy, they began to show signs of abnormalities in their bone marrow. Again, Wiskott-Aldrich syndrome, which had previously been treated successfully by these vectors in Germany. This trial done by Christoph Klein again. Acute leukemia was seen in 7 out of 10 patients, which is a very high degree of conversion to leukemia. And this was between 488 to 1,813 days after gene therapy. So the picture was emerging that these vectors are not safe. So back to Dr. Verma's article. So he said, in spite of the advent of retroviral vectors that cannot replicate, there's still a chance they could cause cancer, and they did. So he said that the efforts to develop alternatives to retroviral vectors should be pursued further. And sure enough, the next vectors were used, as already mentioned, Jim Wilson, who was working on adenoviruses. He decided to use adenovirus for gene therapy in a patient who had a disease called ornithine transcarbamylase deficiency, which is a liver disease in which these patients are unable to handle high protein diets. So, but they can be managed by just keeping them on low protein diet. And when very brave young man named Jesse Gelsinger volunteered to participate in this trial, he had a mild form of OTC deficiency, but he volunteered anyway, and he was given a high dose of adenovirus vector. And unfortunately for him, within 98 hours after being given the high dose of adenovirus vector carrying the therapeutic gene, there was a serious immune response to adenovirus vectors. His body swelled up like a balloon, the massive immune response, and basically his entire, all organs were shut down. And unfortunately, the first death in gene therapy trial occurred in this trial at the University of Pennsylvania. And this paper was published by Dr. Wilson and his colleagues in 2003. It's a fatal systemic inflammatory response syndrome in an ornithine transcarbamylase deficient patient following adenoviral gene transfer. So adenoviruses were not safe. Interestingly, in China, there's a bunch of companies were showing clinical efficacy in a number of gene therapy trials for head and neck cancer. And it was very interesting that none of these were actually peer-reviewed publications. These are all reports in their company websites. So Dr. Wilson actually insisted that this be published. So he asked the lead guy there, Zhao Huipeng, and he still would refuse to publish this in a peer-reviewed journal, except that he agreed to write a review article in Human Gene Therapy, which was published in 2005, where he provided the current status of gene therapy of liver, head and neck cancer with adenovirus vectors, where they were claiming high rate of success. The problem with this trial was, these trials were that yes, they were able to show between 30 to 70% reduction in the tumor size, but there was unfortunately no benefit in the survival. So these patients were still dying of head and neck cancer. And the other problem was these trials were actually repeated in the US on the West Coast. And again, there was no clinical benefit that was seen. So basically adenoviral vectors were abandoned because they did not show any clinical benefit. And then the next group of vectors that were tried is a cousin of a retrovirus called lentivirus. Lentivirus is actually essentially the same virus that causes HIV or AIDS in patients. But this was obviously a disabled vector that was used in a number of clinical trials and showed moderate level of efficacy. So the first trial that was again reported by Alan Fisher, Marina Cavazana-Calvo, and Patrick Auberg in France, they used lentiviral vectors to treat X-linked adrenoleukodystrophy. And again, they treated 2 patients and they showed clinical benefit for up to 30 months. So this was promising. Then they tried a different disease called metachromatic leukodystrophy. This trial was done by Luigi Naldini and his colleagues in Italy. And again, they treated 3 patients and they showed up to 21 months clinical efficacy in this disease. So it looked like this was a better alternative to retroviral vectors. And Wiskott-Aldrich syndrome, which I mentioned before, 7 out of 10 patients developed leukemia, whereas in this case, Luigi Naldini and colleagues in Italy showed that 3 patients actually were disease-free for up to 32 months. So this looked like lentiviral vectors may be a safer alternative. And this trial was done by Philippe Labouche in Paris. They showed this 18-year-old male patient who had severe beta thalassaemia was actually who was given his bone marrow transplant in 2007, actually became transfusion independent. So his disease was, beta thalassaemia was actually cured. So this was good news. And 21 months after gene therapy, the levels of hemoglobin A reached 10 grams per deciliter. So normal is about 15. So he came very close to becoming a normal. So basically he was cured of his disease. They then expanded this trial. This is Philippe Labouche and Cavazana-Calvo to 22 patients, 12 to 35 years, and they all became transfusion independent. And this Trial was initiated in 2013 and was published in 2018. So this lentiviral vectors look really promising. So for 15 to 42 months after gene therapy, the levels of hemoglobin A range between 3 to 10 grams per deciliter, which would be therapeutic. And then 2017, Philippe Labouche and Marina Cavazana treated a 13-year-old sickle cell disease patient. And this trial was done in October 2014 and published in 2017, and showed that this patient, about 48% of the anti-sickling beta globin protein 15 months after gene therapy. So essentially this patient was also cured. Unfortunately, the first patient, that 18-year-old I just mentioned, who received the first gene therapy for beta thalassaemia, 33 months after gene therapy, he's now, of course, 21 years old. This patient began to show clonal expansion of myeloid cells and the transcriptional activation of a cellular proto-oncogene called HMG-A2, which is frequently associated with pre-leukemia. So this is not a good sign that this young patient is now showing evidence of pre-leukemia, which means one step away from developing acute myeloid leukemia. But remember, this took at least 10 years before this happened. And just 4 days ago, this paper was published in January 13th issue of New England Journal of Medicine. This 25-year-old female patient with sickle cell disease was treated with the same vector. This trial was initiated in August 2015, and nearly 5.5 years later, this 31-year-old patient who was diagnosed with acute myeloid leukemia in February of 2021. So this is not looking very promising either. So I'm just going to read what they reported in this paper. They said that 5.5 years after gene therapy, the 31-year-old patient that was diagnosed with acute myeloid leukemia in February 2021. She underwent 3 cycles of induction chemotherapy, which led to remission, but she remained positive for the minimal residual disease. She underwent stem cell transplantation in June 2021, but remained positive for minimal residual disease. She had a relapse with the reappearance of circulating blast cells 90 days after transplantation and underwent additional chemotherapy. However, she later died from complications of progressive acute myeloid leukemia. So I think, lentiviral vectors, the long-term safety also remains very questionable. So I'm just going to very briefly summarize what I've told you so far. These are the vectors that have been used in human gene therapy. So the first group of vectors were used was based on mouse retroviruses. Initially, they showed clear symptoms, clear signals of efficacy in treating a number of diseases: ADA deficiency, X-linked SCID, Wiskott-Aldrich syndrome, and chronic granulomatous disease. But unfortunately, several cases of acute leukemia in every single disease was observed. So retrovirus vectors have essentially been abandoned. Next came obviously the adenovirus. And again, as I showed before, the ornithine transcarbamylase deficiency, the death of Jesse Gelsinger also resulted in the death of adenoviral vectors for all intents and purposes. Although head and neck cancer efficacy was reported, but only in China, it was not reproduced in the US or anywhere else. Lentiviral vectors showed promise, obviously, for the longest time for a number of diseases. And just when we were becoming comfortable with the use of lentiviral vectors for the treatment of X-linked adrenoleukodystrophy, metachromatic leukodystrophy, Wiskott-Aldrich syndrome, beta thalassaemia, and sickle cell disease, the pre-leukemia was reported in 2010. And late last year, this patient has now developed acute myeloid leukemia. And just last week, this paper was published. I just showed you this patient not only developed acute myeloid leukemia, but she also died recently. So back to Dr. Inder Verma's article. Again, this is the last paragraph. He says that in spite of the advent of retroviral vectors that cannot replicate, there is still a chance they could cause cancer. So efforts to develop alternatives to retroviral vectors should be pursued further. So which is where adenovirus and lentiviral vectors were used. But he also said, as should research into site-specific gene delivery. So remember, the reason these patients are developing leukemia because the retros and lentis are actually integrating randomly into the human chromosome, and therefore they're activating these oncogenes, which leads to leukemia. So if you can deliver the gene site-specifically into the human genome, you could avoid this problem. So do we have a virus that can deliver genes site-specifically? And the answer is yes. Fortunately for us, we have, this is again an image taken from an article written by Theodore Friedman in the Scientific American June issue of 1997. This virus is called adeno-associated virus, or AAV. This virus was brought to the University of Florida by none other than Dr. Burns 46 years ago today. Dr. Burns moved here as professor and chairman of the Department of Immunology and Medical Microbiology, where he was until 1984. And then he went on to become the dean of the College of Medicine and vice president of Health Science Center from 1998 to 2002. And then he became the director of the Genetics Institute from 2003 to 2012. And since 2012, he is the distinguished professor emeritus, and we are extremely fortunate to have him with us. And I was very fortunate to have been in his lab for 2 years. And this is the paper he published in a landmark publication in 1990, where he showed that AAV remains the only virus that can integrate into the human genome in a site-specific manner. And this virus can integrate into the human genome. I'm so sorry, my dog is barking. My apologies. So the AAV genome can integrate site-specifically into the long arm of human chromosome 19, 19q13.3 to be very precise. Remarkably, this is the only virus that can do so. No other virus can deliver a gene site-specifically in the human chromosome. And again, as I said, I was very fortunate that I was able to work in his lab for 2 years. And I wish I could go back in time and work with him forever. So here's the summary. As of yesterday, January 16, 2022, 5,107 gene therapy clinical trials have been or are currently being performed worldwide. Retroviral vectors have cured ADA SCID in more than 30 patients, and some cases of X-linked SCID, but have also caused leukemia and deaths in a number of patients. The first reported death in a gene therapy trial occurred with adenovirus vectors. This is Jesse Gelsinger's story. But the claims of efficacy of adenovirus vectors in China need to be corroborated elsewhere. Lentiviral vectors appear to be safer and more promising initially, but their long-term safety has now come into question because of recent reports of leukemia in several patients and in the death of a patient. And this is not highlighted here, but this is a preview of my presentation next month. Just provide this information to date. Actually, as of this morning, 273 phase 1, 2, 3 clinical trials have been performed with AAV vectors and have shown clinical efficacy in gene therapy of at least 8 human diseases thus far. So this is by far the most attractive vector for gene therapy in humans. And AAV vectors are likely to cure a number of human diseases, in the near future. I should also add that without Dr. Burns, there will be no AAV vectors. So as I'm sure you're all very familiar, Dr. Burns is a distinguished member of the National Academy of Sciences. And I know he does not want me to say this, but I'll say it anyway. He is also been nominated for the Nobel Prize. So now that AAV vectors have cured human diseases, this is going to be a well-deserved Nobel Prize for Dr. Burns. And I can tell you personally, every October when the Nobel Prizes are announced, I pray that his name appears on that list, which hopefully will soon. So gene therapy has had its ups and downs, but is likely to cure a number of human diseases, both genetic and acquired, especially with AAV vectors. Although there are a few downsides, which I will be able to present at the next month's meeting. So overall, gene therapy is here to stay, but I would like to end this presentation by showing one last slide. This is written by a colleague of mine in France. His name is Philippe Laboulge, who did the first beta thalassaemia trial with lentiviral vectors. It says primed for takeoff. This was published in Nature in 2013. So gene therapy is finally getting a bumper crop of data that show clinical efficacy after fine-tuning of key parameters that control safety and potency. Supporting evidence comes from pediatrics of 2 life-threatening human diseases. So he ends his this commentary by saying, the development of the field of gene therapy shares many similarities with the history of aviation. Each is based on deceptively simple principles: the introduction of a therapeutic gene into cells and the flow of air over an aircraft spring. Each field was marred by shortcomings and adverse events early on, but in spite of naysayers lacking vision, both fields continued their quest, and now there is firm hope that gene therapy will soon do for medicine what airplanes did for transportation. So again, please keep this in mind, that this is still a very early stages. Gene therapy still is in its infancy, and surely there will be, in all clinical trials, there have always been deaths. Some patients unfortunately will die, but we will learn from each experience, and hopefully gene therapy will cure a number of human diseases in our lifetime. So I'll stop here, and thank you so much. And I'll be happy to answer any questions.
Thank you, Arun.
Thank you, Ken.
So Julie, do you have any results in terms of questions being listed so far?
Sure, we must have some. Congratulations, by the way.
I have a good PR agent.
He's,
Dr. Srivastava.
like you said, he's so humble, he will never say it. But I know of no one who deserves the Nobel Prize more than Dr. Burns.
Unfortunately, you're not on a committee.
All right, well, we have one chat question. It says, what is the time length of longitudinal studies using AAV vectors?
So, this is very interesting, very, very important question. So the very first trial that was done for human liver disease was a disease called hemophilia. And the 15-year follow-up has now become available. And remember, these are all early stages in a phase 1 trial, which is where the objective is not the efficacy. Objective is the safety. So in the first hemophilia trial, no clinical efficacy was seen, at least not long-term, but safety was established. So these patients who were given a high dose of AAV vectors in the early 2000s, 15 years later, these patients still doing well, but no evidence of cancer in any of the patients. So in 270 plus clinical trials, unlike retro or lenti, not one case of cancer has ever been reported with AAV. So long-term safety clearly has been established. And as hopefully I'll be able to show you some direct evidence in February that a number of human diseases have been cured. Now, I should also mention, I'll provide a preview of this, because AAV vectors are so safe, all these, so there are more than 50 companies have been formed. The AAV has now become a multi-billion-dollar industry, actually reaching almost $1 trillion. So all these companies, because AAV is so safe, they keep giving higher and higher doses. And I used to always brag about, AAV may not cure your disease, but it will never kill your patient. And unfortunately, that is no longer true either. So 6 patients have now died in AAV clinical trials simply because they were giving massive amounts of AAV vectors. Just to provide you, just a glimpse of, what you'll be hearing the next time. So a human body contains 30 trillion cells, a total of 30 trillion. But these patients were being given 12 quadrillion particles, which is 700 times more AAV particles than there are cells in the body. So I can only come up with one word, insane. This is just such a heavy dose. Too much of a good thing can be bad. So that all these deaths have occurred in AAV trials because ungodly amount of AAV was simply infused in patients. And there's no reason for that. So short answer is yes, AAV vectors are safe as long as you don't cross. So AAV vectors can be tolerated 3 times the number of cells in the body. In other words, you can give patients, easily you can give 100 trillion particles and it would not do any damage. So I'm not a clinician, but I can tell you, as long as you keep the vector dose low, and hopefully I'll be able to share some data with you how to reduce the vector dose so that you can give these patients safe amounts of AAV vectors.
We have another question here. Karen Mary, go ahead.
Hi. Yes, I was curious about the first 2 examples you gave, Ashanti De Silva and the other girl. I may have missed this, but I'd like to know what was the vector that was used, and also, was it a one-time treatment or did they have to continually give infusions?
Yeah, so answer is a little bit more complicated. So answer your first question. So they were given the retroviral vectors. So that was the first trial. Both Cindy Kissick and Ashanti De Silva received their own cells that had been infected with the retroviral vectors. But this was a less severe form of the disease. But the problem was, for ethical reasons, so these patients were still being given the enzyme replacement therapy. So in addition to the vector, they were also getting what is called PEG-ADA, so polyethylene glycol complex with the enzyme. So initially it was not clear whether the gene was doing the job or is the protein that was being given. But it clearly was, now that they have lived in their 30s and 40s, that the gene obviously was working. So fortunately, none of the patients in the ADA trial died or developed leukemia. Only in X-linked disease of SCID, because they are using the IL-2 gamma receptor, which can trigger leukemia, was the culprit. I hope I answered your question adequately.
Yes, thank you.
Yeah.
Any other questions or comments? Ken, you want to share?
Well,
wait, I'm sorry. I see David Polliger waving.
Thank you for that talk. Would you be able to comment on the relative advantages versus disadvantages in the places for gene transfer versus gene editing? And I'm thinking about sickle cell and thalassaemia in particular.
That's an excellent question. Yes, so more recently, I didn't go there because this was supposed to be an introductory presentation. We talked about the history of gene therapy. But clearly, gene editing is now in vogue, and rather than inserting the whole new copy of a gene, it would be better to go in there and simply edit out the disease gene. So this clearly is something that being pursued actively. As you know, 2020 Nobel Prize went to CRISPR-Cas9 by Jennifer Doudna and Emmanuel Charpentier. So using Cas9 enzyme, they can actually go in and edit the wrong nucleotide in the DNA. The downside to this is still very new technology. It's been less than a year. It's a little over a year actually, where clinical efficacy has been seen for sickle cell disease, for example. They have been able to edit out the mutation, which is the single point mutation in the beta globin gene. But my worry is that, it's a bacterial protein. The Cas9 protein is a bacterial protein. It's a large protein, and it's also highly immunogenic. And all of us get infected by bacteria, and all bacteria contain Cas9, one form or the other. So 89% of humans are actually seropositive for antibodies to Cas9 proteins. So I'm still a little, concerned about the efficacy, long-term safety of CRISPR-Cas9. Just like lentivirus, it took 10 years before we began to see evidence of leukemia. So I hope for patients' sake it doesn't happen, but I would be skeptical. Again, I have to, in full disclosure, I'm not a clinician, so I cannot, intelligently, predict the future. So, but from the layman's point of view, I think introducing a protein that is basically it's a nucleus, it makes double-stranded cuts. So cutting a DNA, in my opinion, is probably not the best idea, and especially one offsite cut in the nucleus, in the nuclear DNA could wreak havoc in the long term. So, and hopefully, if I get a chance, I'll talk to you about, we have developed what we are calling the nucleus-free genome editing. So this is going to be absolutely much safer. And I mean, nothing in life can be guaranteed, right? But you can, try to do the best you can. But my prediction is that, the approach that we and our colleagues have developed would overcome some of those limitations. So yes, so gene editing, again, long-winded answer to your question is that, yes, genome editing would be far more preferable than gene insertion. Thank you for a very insightful question.
Okay, Ken.
Okay, well, I just want to put a PS on some comments that Arun made. He talked a lot about the safety issue, and he made a really important point, and that is that too much of anything is not good for you. And so one of the challenges is to try and make the AAV vectors, for instance, more efficient so you don't have to give such a heavy dose. And I would say that Dr. Srivastava has been a leader in the field in terms of developing modifications to the AAV vector, which make it much more efficient in terms of transferring genes to the cells. That's a really big deal for the field. And so these are all the kinds of issues. Back in 1996 or 7, I was asked to go to the NIH by a director and talk about whether AAV was ready to be used as a vector for gene therapy. And I said, it's going to be a great vector, but we don't know anything about the biology of the virus. We know a lot about its structure, but we don't know how it interacts with the body. And that turned out, in fact, to be critical in terms of developing AAV vectors and others that actually function usefully in a clinical setting. So this is a long process. And the trouble we have especially in this country, is we'd like results yesterday. And so the notion of going 20 years or so to see something develop is a difficult one to deal with sometimes. But in fact, this field, I think, demonstrates how that actually works. I'd say the other thing that this is a good example of is say we're working, we did a lot of work with the basic molecular biology of AAV. And of course, the problem was, from a lot of people's point of view, is it doesn't cause any human disease, even though we all get it. So people used to say, what's the point? Why are you wasting your time studying a virus that doesn't cause disease? Of course, the fact that it might be a virus that cured disease didn't really occur to anybody, but I think it's a classic example of the utility of fundamental research. That's what we were doing, and the results we see with the use of the virus now as a vector. So I'd like to thank Dr. Srivastava for that exceptionally clear lecture. I enjoyed it because a lot of the people he cited are personal acquaintances and friends, and so it's always kind of heartwarming to see that kind of situation. So thanks again, Arun. Who's next week, Julie? I think we have, is this Dr. Munoz?
Yes, CRISPR and
We're gonna,
plant
yeah.
CRISPR and genetics.
Next week, you'll learn how to deal with genetically modified blueberries. And of course, if you look at the foods you buy, there's always on the label, it frequently says non-GMO. And the amusing part to me is that for eons, farmers have been tinkering with the genetics of various crops, and they keep looking for mutations that work better. And they don't have any idea what they've done to the plant, except it does something better. With GMO, you know what you've done, but for some reason that seems to make people more nervous, especially in Europe. So it's an interesting conundrum for human behavior. Anyway, thank you all very much, and we hope to see you next week.
Thank you, Ken.
Thank you, Arun.